I'm very thrilled about this because for those of you who don't know me, I'm a neuroscientist. So as you are engineers and build systems, I reverse engineer them. For me, creativity, I deal with creativity in the brain, and I've always thought that there should be much more crosstalk between the different areas and people who concern themselves with the process of creativity. So to jump right in, because the talk is packed on the essential components for a neural mechanism of creativity, let me give you a sneak preview of the things to come. For about 10 minutes, I'm going to spend some time with conceptions of creativity as we deal them in cognitive science and cognitive psychology, even in social psychology, but particularly also in neuroscience. I call them theoretical duds because that particular section, about 10 minutes long or so, really what this is a sustained, uncompromising demolition project of all, to sanitize you, of all the bad habits we have for thinking about creativity. It's not only that many people have an overly romantic, fluffy view of human creativity, but if you want to hunt mechanisms, we need something better than we have. Once I'm done with that, I'm going to introduce you to two frameworks that I think should form the bedrock on which to anchor any search mechanism for the neural mechanisms or the mechanisms of creativity, period. There are more in terms of neuroscience, but I concentrate on these two because I think you can relate to them better. And the talk will not have much neuroscience in it. I will stay very computational in this. The first one is the evolutionary framework, which is part and parcel of creativity research, and it's been for a long time, but it's never been really applied to setting up experimental protocols in neuroscience. And the second is an emerging framework that is starting to dominate all of neuroscience. I'm going to introduce you to this, and it's fairly new. It started about 10, 12 years ago, that we think that the prediction machinery of the brain that you have is a central organizing principle of all of cognition. That sounds like a big statement, and it is. But some people think that this is a leading candidate for understanding why your brain became so complex as it is. You have, there are some references for a few things related to the talk if you want to read more in depth about it, and a book and a special issue of the journal Methods that I organized as an editor a few years back, and that has some of the methodological constraints that we're dealing with in neuroscience when we're looking at creativity. Let's jump straight in, the theoretical duds. Human creativity, our ingenuity, is something very special. And there must be something in the brain that makes it so. And so far, over the last 40, 50, 60 years, we have unfortunately hung on like grim death to a few outdated concepts that desperately need their neuroscientific funeral. I have, over the last few years, tried to provide these in order to get to a more sane, commonsensical view of what creativity might be in the brain. The first one, you're very familiar with this one. I call that the brief and frightening reign of the right hemisphere. Although most of the neuroscientists and cognitive psychologists know that creativity has nothing to do with the right hemisphere, if you were to go outside and stop the next person outside here in the rain and ask them, tell me what you know about the brain and creativity, they'll tell you something about the right hemisphere. Although no one pledges any allegiance to this rather stunted idea, there is still a reason why to put this first in my demolition project here. The first one is the ghastly side effects this idea had in the general public. As I said already, it is probably the one thing that anybody would remember about creativity and the brain. Of course, most people who work in the neurosciences know that this is not the case. But you can, of course, go to any bookstore and go to the self-help section and find yourself a book on a business seminar to tap into your right brain potential. I think this is an idea that should be treated like nuclear waste and buried for a million years. And I think we've done this. But there is a basic underlying error in thinking that goes much deeper than this, and this is phrenology. And we neuroscientists ought to be very cautious about pinning a complex psychological process or processes like creativity on a single brain area. Whether it is the right hemisphere or some 428 million neurons in your parietal cortex. This is just simply not how the brain works in terms of networks. The current front runner in this mad dash to identify creativity in the brain, of course, is the frontal cortex, and that idea is just as dumb. Because you have to look at the brain as a whole. The underlying error here is to locate things. It's phrenology, we got to get away from it. The second one, you're probably also familiar with it. I call that the rise of divergent thinking and fall of everything else. This was an idea by J.P. Guilford about 50, 60 years ago, and was a good idea 50, 60 years ago, because you had to get the research program going of looking at experimental studies of creativity. But somehow in the last 20, 30, 40 years, this theory of divergent thinking morphed into a theory of everything, meaning it was the only experimental paradigm anybody bothered implementing in an experimental protocol. That meant for the last 50 years, we really had an experimental study of divergent thinking, whatever that is actually, and not an experimental study of creativity, which we need. The main problem is that divergent thinking is what I call an amorphous monster. It is a compound construct that includes just about every single mental process that we have identified. From all perceptual processes, categorization processes, from working memory, reference memory, long-term memory, to attentional processes, everything is in it when you do divergent thinking. So, of course, what happens when you give anybody, a participant, as we call people in research, one of those divergent thinking tests, you know, one of those open-ended questions that you get in a Torrance test or the remote associate test. Tell me all the things that you can do with a safety pin or with a brick, and then put them on the functional MRI scan. Essentially, the whole brain lights up because all of the processes that you need for divergent thinking are included. I am similarly pessimistic, famously so in my neighborhood, of identifying all of the other wild goose chases, the dead ends that we've pursued for the last 50 years that lead us to no place good, not in neuroscience, not about creativity. Here's a list of them. I'm sure you know many of them. That creativity is associated with low arousal or with defocused attention. I'm sure you've heard this. Or lateral thinking. I don't even know what that would be. Or altered states of consciousness. And then, of course, you have that thin line between the mad genius and creativity, where you associate creativity with mental illness, schizophrenia, autistic savants, and bipolar disorder mostly. What's the problem with them? It's very simple. They are not selective enough for creativity. The exact opposites of them are also sources of creativity. You can be creative in a state of high arousal. I have been. You probably have been too. Much of creativity is produced by focused attention, not by defocused attention. I actually don't know what the opposite of medial thinking, I guess, supposed to be, lateral thinking. I don't even know what the opposite would be. And then, of course, you have altered states of consciousness and mental illness. I've tried to make this point for the last decade almost, that this association is exactly in reverse. The vast majority of creative products that we humans have put on this planet have been put on this planet by people that don't have a mental illness, that cannot be classified in a DSM, the Diagnostic and Statistical Manual of the American Psychological Association, which is the Bible of mental disorders. And the vast majority of people with mental disorders, they have mental disorders, people. They are not creative, save for the few autistic savants and for the few people with bipolar disorder, like Kafka and Schubert. Yeah? The vast majority of people who are mentally ill are not creative. The association of creativity with altered state of consciousness and with mental illness is negative. These concepts are useless for hunting neural mechanisms of creativity, and we have got to give them up. Okay. Now where do we throw them? We all binned them. I want to introduce you to two paradigms. There are about 4 or 5 or 6 that I'm playing around in my head and developing that has been my occupation for the last 5 to 10 years. And I introduce you to 2 today, which I think should form the bedrock on which to anchor a serious search for the neural mechanisms of creativity. That means how your human brain produces creativity. The first one is the evolutionary framework. Part of the reason for the disciplinary insolvency of the neurosciences as they deal with creativity is the reluctance or inability to come to grips with the evolutionary framework, with a reductionistic research program that looks at mechanisms of how we are creative. I have talked to many people that I would think are sound materialists and don't believe in ghosts. And even they tend to cringe in horror at the thought that human creativity can be reverse engineered without residue. It is clearly one thing to commit to a mechanistic research program, which we neuroscientists all do more or less, and it's quite another to accept all the inevitable consequences that comes with such a view. And so the first thing that I'm going to look at here is the evolutionary framework. The sharp end of that stick is a debate, acrimonious debate, heavily overheated, about how far Darwinism extends upwards into culture. That debate should not concern us, at least not us neuroscientists, if we want to build neuromechanism of creativity, because there is a common denominator, and that common denominator is a consensus that culture is an evolutionary system. The question is what kind of evolutionary system it is. I want to work out first this common denominator by taking you back a little bit into evolutionary biology. And then I'm going to go through differences in evolutionary algorithms for culture and the biosphere, for the infosphere and the biosphere, and then work out the differences and how we can explain them, how the brain accomplishes them. So the first one, I have to run you down by the main 2 different sets of evolutionary algorithms, and that is the variational system and the transformational system. The variational, of course, being the Darwinian system, and the transformational system being the Lamarckian. And I'm sure you've heard this, that many people claim that culture, and by extension human creativity, is a Lamarckian system, which I think is a misguided idea. And then we're dealing with the idea of blindness and the idea of sightedness in evolutionary algorithms, particularly for us. Partial coupling, how we couple variation to selection, and how your brain does that. And then I'm going to have a slide on the differences in the 2 evolutionary algorithms. Let's start with the patterns of change. Here you have a pattern of a variational system of evolution. If you look at it, at the first side on the left panel here, this is a Darwinian system. A Darwinian system is a system that is based on variation. And because it's based on variation, it's based on selection. The basic underlying idea is that you have individuals in that population that vary in their fitness. Evolution occurs because some of the variants, some of the mutations have a higher fitness value. And what evolution is in a variational system is a statistical distribution change in the population of those towards those individuals that have a higher fitness. At the end, you get evolution, if you see this on your right panel. Here you have a Lamarckian system. This is a Lamarckian transformational system. It is a system of evolutionary algorithms that works in a very different way. And it's not the one, as you all know, that works in the biosphere. The Lamarckian system, however, is still a set of evolutionary algorithms, and it works the following way. Here, individuals in a population do not vary. It is not based on variation. And therefore, there's also no selection process. It's an evolutionary algorithm that is based on adaptation guaranteeing instructions. These instructions do not come from on high. It is a system without a designer. The instructions come from the environment. But because there's no variation and no selection process, the process consists of no waste and no competition. All of the individuals, if you see that on the left panel, are transformed in lockstep in the direction of adaptation. Meaning, the instruction from the environment guarantees that any change is adaptive. That's not the case in the Darwinian system. Okay? It's very clear that culture is not a Lamarckian system. It's not a Darwinian system. It's not a Lamarckian system in the sense that we vary. We all know that. And culture varies. Everybody agrees, even those vehemently opposed to an evolutionary approach to human creativity, that culture is a variational system. Now we come to the matter of blindness and sightedness, or partial coupling. And this actually hits the same spot from the same angle. From a different angle. Darwinian blindness, you all know that genetic algorithms are fundamentally blind. What we mean by blind is not random, because the algorithm is not random. The mutation is not random. It is blind in a sense that is undirected with respect to selection. We call that an ex post facto algorithm. An algorithm where the error of causation only goes one way, from the genotype to the phenotype, never the other way, never from the phenotype to the genotype. Okay? That means variation is completely uncoupled from selection. What that means is that variation first happens and is completely and totally and utterly over. And then you have a process sorting it. In an algorithmic function, you can describe this as a coupling parameter of that algorithmic function being set to 0. A Lamarckian system is the exact opposite. Remember that here you have instruction, adaptation that is guaranteed by the instruction. Because it's not based on variation, blindness plays no role in it. It's a process that is 100% sighted. Adaptation is guaranteed from the start. For this set of algorithmic functions, evolutionary algorithms, the capital parameters are 100% or set to 1. All the evidence we have, and I think the best reference we have is Richardson Boyd here in 2005, their book, is that human creativity fits neither. It is neither blind, obviously, and it's neither 100% sighted. Otherwise, we would have to consider creators a special class of prophets if it's 100% sighted. Okay? We have here a variational system. Culture is a variational system with partial coupling. Culture is a system where units are inherited. However you define these units, memes or not, doesn't really matter. It leaves an accumulative change over time, a trail of accumulative changes. And by extension, this is of course produced by our brain, that means human creativity. This common denominator is unobjectionable for most people, even in the field, even those opposed to a Darwinian approach. But the cultural evolutionary algorithm is different than the biological evolutionary algorithm. It has 4 features that I like to point out, and I go through them then for the next 30 minutes. The first, degrees of sightedness. This is a no-no for biological evolution. They have no sightedness. They're blind, by definition. That's a Darwinian algorithm. Then there's a second problem in thought trials. Darwin named his invention, his discovery, evolution by natural selection, because its fitness function is in the environment. But if you have a thought trial, if you produce creative ideas in your head, you by definition go into uncharted territory. How you decide ahead of time what is adaptive in that solution space? You have to set, your brain has to set somehow merit criteria for a fitness function that has to operate in a hypothetical solution space. In the real environment, there you can see survival. But how you decide that in a hypothetical solution space? The cultural evolutionary algorithm has found a way to do it. Biology didn't. Next difference is scaffolding. I'll talk about scaffolding when we get to this. This is something the biological evolutionary algorithm cannot do. And that is because of the ex post facto requirement of that algorithm. Every single iteration of the process has to be instantiated and survivable in its own right. Not the case in your head. And finally, the one thing that is mostly recruited, abducted really, to make a claim for a categorical difference between biological creative systems, evolutionary algorithms, genetic algorithms, and what you do in your head. The idea that we have intentions and foresight, which we all know famously the biological evolutionary algorithm does not. What we have to ask ourselves is, how does the brain accomplish this? those four things: scaffolding, intentions, sightedness, and how does it build a fitness function in a hypothetical solution space. And there we come to a new and very exciting paradigm that is permeating all of neuroscience. What I want to do here in the prediction framework is tell you first what is meant by a proactive brain. Then I'm going to talk a little bit about the cognitive domains that have recognized this as a central organizing theme for all of cognition. Then I'm going to give you a specific example of how a neural emulator finds solution in event spaces. I use the motor system because that's how the system, computationally speaking, evolved. And then we're going to extend this prediction to offline emulation and creative thinking. So let's start right away. What is meant by a proactive brain? We are starting to understand how big this thing is. The understanding that you do predictive processing in your brain. That means that you generate expectations and anticipate. And in fact, our interactions with our environment, we have to deal with infinity. The amount of information in the world is, if not infinitive, it's near infinitive. In order to behave purposefully and in a timely manner, we must constrain infinity. The brain seems to be doing this by continuously and automatically generating predictions, constantly, that anticipate events. That means constrain them. Even when you're not engaged in a task, when you do mind wandering, the brain is always in drive mode, because you never know what comes next, furnishing expectations. These predictions then meaningfully inform all perception, all action, at all times. Your brain is a prediction machine, and that prediction machine is the basis of our intelligence. Or so this paradigm sees it. That this is not an optional add-on, a luxury that maybe we have but not the next chimp. You'll see when you understand sensory motor timescales. And anybody who's in robotics doesn't need much explanation for this. You will understand this right away. Motor execution and perception needs a lot of processing time. Your motor system is a hierarchical complex system. It has several different motor structures in the cortex. And there are several others subcortical: basal ganglia, cerebellum, and the thalamus, the red nucleus. And before you send down the specifics of a motor plan down the cortical spinal tract so that you move, half a second has already gone into the preparatory calculation time. It takes a lot of time. Perception is the same thing. Let's say I make a movement. If I actually were to wait for feedback for actual sensory processing, I would have to pick this up with my hands. It has to go down in my spinal cord and send up dorsal columns in the back of the spine up to the various centers, including the cortex, that then needs to produce a complex picture of the environment. If the interaction of the world with the world is actually based on direct engagement, the whole thing would be way too slow. And we know that. We know that this is not a description of how you interact with the world. You move and you get feedback, and from that feedback you move again. This is not how it works. We know it cannot possibly be that way because you move too fast. The only way to solve this, of course, is to predict what you are going to find. And this is exactly what the motor system does. It's a prediction system. Emulation allows the speed to increase beyond real-time processing. What this means is that the motor system constructs an internal model of the entire sensory motor loop, which includes a forward model and a controller, an inverse model. This streamlines the whole process into comparing the predicted environment from the sensed environment, which makes it, of course, much faster. Your entire motor system fundamentally operates on prediction. The first cognitive domain where we understood this was in the 70s, in learning, that we understood that the basic principles of learning depends on a prediction system. This is an example. There are other systems. This is just an example I put up here that of classical conditioning. This is the Riscola-Wagner model. but it also works on operant conditioning. It says essentially that the basics of learning, anything that you learn in the environment, depends on the predictability of the reward. The degree of unpredictability, which is the degree of surprise, determines the rate of learning. If the error, that's the prediction error, if the prediction error is positive, that means you get a higher reward than you expected, you learn. If learning ceases, when the prediction error falls to 0. The difference here is that you would have thought prior that if you get a reward, you get reinforcement, you learn. But that's not the case. If the reinforcement matches your prediction, there's no learning. You have to have a reward that is surprising to you in one direction or the other, whether you have learning or extinction. That means the basic principles of learning depends on you anticipating the kind of reward that you're getting. It's a prediction system. The same with memory. And people find it surprising when we tell them that we have reconfigured the entire idea where you have memory in the first place. Memory is reconstructive and associative, we know that. Make it essentially the same thing than imagination. You think of memory as being about the past and prediction about the future, but that's probably not the case. The purpose of memory is to feed your neural emulators. The whole point of memory is not reminiscing about your first kiss. It's about how predicting how the next one feels. The purpose of memory is to make information available for simulation. I can give you 10 more examples, learning and memory being the biggest ones, but it also has to do with attention capture. We all know you do not attend to things that you do not expect to see. Theory of mind, imitation, observational learning, all of these domains have understood that the basic underlying principle of cognition evolves around you anticipating. There is nothing, not a thing that you do without trying to render a prediction. If you go to the elevator and press the elevator button, you have a prediction of how long it would take before the elevator starts moving. If that is violated, that's a violation of a prediction, you would immediately look around. What's wrong with the elevator? You cannot possibly be surprised unless you have a prediction in your head, which you do. I need to give you a specific example of how this runs in the motor system, because there the system is worked out the best. And if you're in robotics, you know parts of this, and this is not going to be new for you. In psychology, we know this as the Ideomotor Principle. It comes from William James, about 120 years old, and it is the basic idea that actions are represented like any other event, which means in terms of perceptual consequences. We call it the common coding theory. What we mean by this is the following thing. You understand the world only through your sensory systems. And that's it, only through your sensory systems. That means you have to understand your own actions also through your sensory system. Your motor system cannot explain to you your motor system. You have to sense it. That means you have to have a representation of a motor plan in a sensory format. Otherwise, you cannot understand your own actions as being your own. Your motor plans take time for computation and execution. We know that. I explained that already. During that time, we think that the carbon copy, which we call an efference copy, of the plan, is sent to consciousness, which provides you prior knowledge of the upcoming action. You will see that this is a very important concept to explain something else later on. Keep this in mind. I want to be a bit more specific about this. Several motor regions of the motor cortex in the frontal cortex send an efference copy, which essentially is a predictor, to the sensory regions of the parietal cortex and the temporal cortex and a few other places. What that does is that it co-registered the current motor instructions with the current sensory maps of your body. And what this does, this is the forward model of the neural emulator. What this does, it converts the motor plan into a representation that predicts the sensory consequences of the planned action if you were to execute it. Which means you get a preview of what you are about to see and feel if you were to execute your own motor plan. Okay? That is the forward model of the neural emulator. We know that this is not what you do because of the high dimensionality of your motor system. Your motor system is so complex that you cannot figure out a motor plan ahead of time with any specificity, simply because you have degrees of freedom that renders this essentially an infinite process. If I grab this cup here, any twitching I do on my biceps more, I have to do less on my shoulders. We're talking about millions of fibers here. Okay? So what you do is a very common solution in engineering. You build an inverse model, a controller, that gets hold of the problem from the other end. It asks what motor coordinates would I need in order to accomplish the goal. What you then do is that the inverse model starts the process. The inverse model generates a first pass, an efference copy, which goes to the error predicting forward model to generate a preview of the sensory consequences. If they match, I go ahead with the motor plan. This is an optimizing procedure that the motor system operates. As the motion unfolds, both converge, the predictor and the controller, on this motor plan. Now this sounds very complicated, but this is essentially what your motor system does. Your motor system is a Bayesian inference machine. And we know it's a Bayesian inference machine. All people in motor neuroscience have accepted this. The interesting thing is that the prediction system here in the motor system has been accepted by almost all other cognitive systems, and they also run simulations on whatever it is that they are computing. So let's go to offline emulation when you do creative thinking. The motor system produces emulation online. As you proceed, it emulates only milliseconds ahead, as it recalculates the motor plans and its consequences as you proceed, right, on ongoing behaviors. But you have an explicit system, not just an implicit system. You have two entirely different information processing systems in your head. The explicit system has flexibility because it has a working memory buffer, and with a working memory buffer, you can consider several alternative hypotheses. The implicit system cannot do this. It's a concrete operational system that does not represent anything hypothetically. It considers everything true. Only your explicit system functions in that capacity. The explicit system here, internal models, can also produce representations of your emulated future offline and in hypothetical solution spaces. These explicit predictive processes exploit the same computational toolbox than the motor system. That means they have an inverse model, a forward model, and they converge. This feed-forward mechanism is pervasive in the brain. And this is where things become interesting for us here in this talk, for you, for us in neuroscience to deal with creative cognition, and that is in creativity. Now, having outlined, even in just the skeleton broad strokes here, the prediction system of the brain, which we are starting to understand is a major organizing theme in neuroscience. Let's apply this to the four differences that I outlined earlier between a cultural evolutionary algorithm and a biological evolutionary algorithm. That you understand these differences, because now when you put everything in terms of prediction, you can see where the sightedness comes from, right? But let me work this out anyway. The first one changed the variation process. The question now becomes, if you let the prediction system flow into an evolutionary framework, the question becomes of how prediction produces degrees of sightedness or gives direction to the variation process. The second question has to deal with the level of selection and the fitness function. How does a predictive goal representation, and this is the key phrase here, the predictive goal representation, sets merit criteria for a fitness function that must operate without environmental feedback, without actual feedback from the environment during thought trials? How do predictive goal representation allow for the formation of a scaffold that you can jump over unviable intermediate forms? And there, of course, you can also see the direction on which, from where the answer would be coming from. If you throw a line to the other side, of course, you can hang a line onto it, and you can put a scaffold on it. Okay? I want to spend more time here on the last one. how the prediction machinery of the brain, the explicit system specifically, produces the experience of intentions and foresights that human creators have and that we all agree your computer programs don't, right? And the genetic evolutionary algorithm that runs the biosphere doesn't, right? But you do. Let's start with a degree of sightedness in the variation process. Essentially now, this is a straight line, linear thinking of how you would connect these two. Once you connect these two, this makes sense. You have a bunch of executive processes that can configure the neural emulator. You feed all kinds of things in it: context, memory, folk wisdom, prior experience, domain-specific expertise, and so on. Then the emulation produces a predictive goal representation. This is, of course, a guess. That's what a prediction is. It's a guess of a likely outcome. And that, of course, can be used to guide the variation process so that you produce variants that have a higher fitness level from the start. This is essentially what a heuristic is. A heuristic is a guess. It's a guess based on prior experiences that you make a prediction, and from that on prediction forward, the variation process is constrained. It is no longer blind. The predictive goal representation is also the key to understanding how you build a fitness function in a hypothetical uncharted solution space. The parameters of that goal representation would be the basis for this, of course. A predictive goal representation can also set the merit criteria for a fitness function in your head, and your brain apparently does this. Thought trials need that special mechanism because a selection process here doesn't have an environment that actually selects or sorts by fitness or adaptivity. But as soon as you have a goal representation in place, which we generate all the time on just about everything, that's the whole point of the paradigm, the exploratory activity of the explicit system in a creative endeavor, in a creative process, can in principle proceed, computationally speaking, exactly the same as it does in a motor system. You let the predictor and the controller converge on the solution of the problem. Scaffolding. Scaffolding also has a very straightforward explanation once you understand the brain's predictive system. In biological evolution, each iteration of the creative process must be instantiated. I've heard this morning a few talks on evolutionary algorithms, and they're all genetic evolutionary algorithms, which means they have a coupling parameter of 0. Any of the variation process that is guided comes from the interface. That means the creative person using your programs. Yeah? But of course, we want to know how you do this for yourself. How does the person doing this for your system that you're creating, how do you do it here? Okay? In the biosphere, this must operate on individuals that are made flesh. This is the ex post facto requirement of biological evolutionary algorithms. But thought trials in your head or the cultural evolutionary algorithm is not limited like that, because you make predictions. And once you make a prediction, a predictive goal representation that you project into the distant future acts like a beacon of light that can be used to anchor a scaffold. It's just like an anchor that you throw to the other side, attach a line, and then you got a scaffold. This doesn't work in biological evolution because of the ex post facto requirements. Cognitive scaffolding, things that you do as a designer, as a creator in your head all the time, can temporarily support design elements in your working memory buffer where you imagine this, put it aside, and let it flow into the next iteration of the creative process of the algorithm. You can support design elements that are not viable forms in their own right. This doesn't work in biology. This opens up regions of design space that you cannot reach with a genetic evolutionary algorithm. The one thing I'm most interested in: intentions and foresight. Biological evolution, as we all know, famously so, is not teleological. It serves no end. Its designs are neither premeditated nor deliberately initiated in response to some perceived need. It is a blind, dumb, stupid ratchet. Evolution, selection, inheritance. Evolution, selection, inheritance. Evolution, selection, inheritance. Wherever it walks to, it walks to. Part of the reason why the evolutionary framework, why people are so uncomfortable with this, once applied to the human brain, is the argument that human creators don't do that. By contrast, so runs the argument. Einstein, Picasso, and Michelangelo, they act on purpose, don't they? They don't do random. They don't do blind. They create with intent and with an objective in mind. That's all very fine, and this probably appeals to your intuitive categorization of mind and machines. But of course, I'm a neuroscientist, and that's not an explanation for me. I want to know what an intention is. I want to break that beast down as a neuroscientist, because that's not where I'm going to stop my questioning. And of course, what that means is we're going to have to look at the brain's agency system. How do we form intentions? How do we have foresight and act on purpose? How do we get that experience? The current thinking on the brain's agency system is based on predictive processing, obviously. Obviously, I say, because to experience yourself as an independent agent so that you think that you act on purpose, that you have volitional control over your own actions, you must have advance notice that you are about to do something. If you do not know what you're going to do next, you would be surprised by your own motion. If you're surprised by your own motion, you will not get the feeling that you're causing it, obviously. So how do you get the advance notice that you're about to do something? And I already told you the answer 10 minutes ago. Let's go through it again. This advance notice is provided by the predictive machinery of the motor system because it constantly predicts and gives you a heads up on what you're about to do, what your motor system is about to do. The mechanism here, essentially, we think, is the carbon copy of the motor plan that is sent to consciousness, the efference copy, which is an exact copy of the motor plan, except for it's not sent down to the muscles, it's sent to consciousness. It predicts the sensory consequences of the upcoming action, and you become aware of it. In neuroscience, we think that this is the representation of an intention. It is knowledge, sensory knowledge, of what you are about to see and what you're about to feel and hear when you do what your motor system already decided to do. The sense of agency in this view is a misinterpretation of neural activity as a conscious intention, when in fact it is a representation resulting from the simulation of possible motor outcomes. The illusion of intention, this is the right word really, the illusion of you acting on purpose, comes from the same source than your movement. The illusion of intention and foresight in human creativity is created by you becoming conscious of an efference copy that is generated by your thought trials. Intentions, in that sense, are themselves the product of the brain's prediction system. The biological evolutionary algorithm does not do that because it does not predict. But it has produced a machine that does exactly that. It essentially is an improvement on the biological evolutionary algorithm. But it can run algorithms, evolutionary algorithms, with a trick, because it makes predictions. And because these predictions are based on prior experiences, they have a greater chance than not to be right. They can flow into the evolutionary algorithm. And the cultural evolutionary algorithm looks different than the biological evolutionary algorithms, the one that you run in your head when you run thought trials. When you do what we call in the motor system emulation chaining, that means you run several iterations of a thought trial on a hypothetical fitness function. This is essentially what your motor system does when it chains emulations, when it chains predictions, when you look at a chessboard and you figure things out 4 moves ahead of time. That's emulation chaining. So wow, I'm on time. That's my last slide. When I see my Phoenicians, I always know I'm on my last slide. Let me summarize this. Of where we are in cognitive neuroscience, in cognitive science and in neuroscience in general, when thinking about the creative process that we engage in. Forget divergent thinking, lateral thinking, alpha enhancement, low arousal, altered states of consciousness. These are all theoretical duds. I think with several reviews that I have published in the last few years, I think, fairly conclusively shown that we have to give up these dead ends. The review of the empirical data shows that all proposals on the neural mechanism of creativity fall, all of them, as soon as you generalize this to creativity as a whole. These are false categories. And these are false categories because divergent thinking you also do in normal thinking, whatever that is. If you want to differentiate something from normal thinking from creative thinking, you better have something that exists in one box and doesn't exist in the other box. You cannot say creativity is X when that X also applies to non-creative thinking. And that is the case with all of the proposals currently in circulation. Second, we got to anchor the new search for the neural mechanism of creativity on things that we know for sure are creative, evolutionary algorithms in this case. And we don't have to go through the acrimonious debate on how far Darwinism reaches up into culture. There's a common denominator that we can all agree on, and that needs to be applied to the human system, to your cognitive processes. And that is the consensus that human creativity is a variational system with a coupling parameter that is neither 0 nor 100%. And this must form the basis for experiments in neuroscience. I have no problem if you call the cultural evolutionary algorithm a Darwinian system. Whether you're going to call it a Darwinian system or not depends primarily whether you're a lumper or a splitter. Whether you would agree that a variational system can have some sort of coupling and still call it Darwinian. Other people are very adamant about not calling it Darwinian because it's cited. And that would be correct as well. And it doesn't really matter, as long as we understand the common denominator is in place. I would think, to be honest with you, that if you don't run evolutionary algorithm and you're dealing with creativity, you're wasting your time. This is essentially the system, the only system that we know that produces creative products. And we know that for sure. Look at your own floor plan, your own body. It's a very creative production. Your brain does a variation on the theme, but it's not something categorically different. You run evolutionary algorithms that have different parameters to them than the biological one, but that doesn't change the fact that you come with a bottom-up evolutionary algorithm when you are yourself creative. The prediction system is essentially a system that can help with understanding of how your brain makes these changes to the parameters of the algorithmic function. Because the biological system doesn't have a prediction system, you do. Prediction is a central organizing principle for all of cognition. That we do understand in neuroscience. And it provides compelling leverage about how brains exactly run thought trials. And then finally, the last one is that predictive goal representations, this is a key phrase here. You constantly generate a goal prediction. And this is, of course, a representation. And so a predictive goal representation explains the upgrades to the biological evolutionary algorithm, including sightedness, scaffolding, intentions, foresights, and how you establish merit criteria for a fitness function. That's it. Thank you very much.